This video is about qualitative analysis of organic compounds. It relates with the detection of various elements which is present in organic compounds. So this is a very simple part, but many of the students tend to ignore it. But there are questions which are being asked year on year from this particular topic. So being a simple topic, it shouldn't be ignored and it can be scoring if at all it comes in the examination. On that note, let's start with qualitative analysis of organic compounds. Now, in this part, what you have to remember the confirmatory test for the elements, its associated reaction, and the compound which is formed in the reaction, along with the color change, if any, and also the formula of the compounds which is formed in the reaction. So let's start with the first and the most important element of organic compound, but of course carbon. So element carbon is detected by copper 2 oxide test, that is cupric oxide test. The reaction is simple. The copper oxide reacts with carbon, and on heating carbon oxidizes to carbon dioxide and the cupric oxide reduces to copper. So basically cupric oxide acts as an oxidizing agent over here and oxidizes the carbon to form carbon dioxide. So this is the detection test. Now the confirmatory test would be the carbon dioxide which is formed would be passed through lime water, that is CaOH twice, and the lime water would turn milky if the carbon dioxide is present. The associated reaction would be CO2 reacting with lime water produces calcium carbonate along with water, and the milkiness of the solution is due to the formation of CaCO3, that is calcium carbonate. So in a nutshell, a simple point to remember that carbon in the qualitative analysis is detected by copper 2 oxide test, and it is confirmed with the release of CO2 gas, wherein CO2 gas reacts with lime water, and if the lime water turns milky, it's a confirmation for presence of carbon. Apart from carbon, obviously the other important element is hydrogen. Even hydrogen is detected by copper 2 oxide test. Here the copper oxide reacts with the hydrogen, and again hydrogen oxidizes to water and the copper oxide reduces to copper. So again over here the copper oxide behaves as an oxidizing agent and oxidizes the hydrogen to water. The confirmatory test would be the water which is formed, its droplets will appear on the cooler part of the ignition tube and also turns anhydrous CuSO4 blue. So the reaction associated with that is simple. Anhydrous CuSO4 is white, but when it comes in contact with water, it gets hydrated to form blue vitriol, which is CuSO4.5H2O, and hence the blue color becomes a confirmation for the presence of hydrogen. Next is the detection of nitrogen. Now for detecting nitrogen, sulfur and halogens, we have to prepare one extract called Lasine's extract. The Lasine extract is prepared by reacting these elements with sodium, and the corresponding Lasine extract is then treated with some other compounds for the detection of that element. So let's see for nitrogen. The Lasine extract is prepared by reacting sodium with carbon and nitrogen. So on heating together, it forms sodium cyanide, which becomes a Lasine extract for nitrogen. So even this question could be asked. The Lasine's extract for nitrogen is sodium cyanide, that is NaCN. The confirmatory test here is the Lasine extract which is prepared is treated with iron sulfate or ferrous sulfate in alkaline solution. The solution is first boiled and then allowed to cool. On cooling down, it is further treated with ferric chloride in presence of concentrated HCl. So overall, if it produces blue or green color, it's a confirmation for nitrogen. Once again, The lysine extract is treated by ferrous sulfate in alkaline solution. The solution is first boiled and allowed to cool. The cooled solution is then treated with ferric chloride in presence of concentrated HCl. And the blue or green color is the conformity test for nitrogen. Now let's see the associated reaction. First thing, the ferrous sulfate reacts with alkali to form ferric hydroxide and sodium sulfate. The ferric hydroxide so formed reacts with the lysine extract of sodium cyanide to form Na4FeCN6 complex and NaOH is reproduced. Now, this complex is named as sodium hexacyanoferrate because Fe is in +2 oxidation state. Sodium hexacyanoferrate. Now, this complex of sodium hexacyanoferrate in +2 oxidation state of Fe is then treated with ferric chloride in +3 oxidation state, and this produces a complex of iron in +2 as well as +3 oxidation state. This Fe which is outside the complex is in +3 and this Fe inside the complex, that is in +2 oxidation state. Hence this particular compound is called ferroferricyanide. Ferroferricyanide. Or in IUPAC it is named as iron hexacyanoferrate. And when we write the IUPAC nomenclature, we write iron Roman number 3 indicating ferric, hexacyanoferrate the Roman number 2 indicating oxidation state of Fe. And this particular compound, look at the formula very carefully. Fe4 FeCN6 thrice. Fe4 FeCN6 the whole thrice is named as Prussian blue because of its color. It's named as Prussian blue. To summarize, in the detection test of nitrogen, the lysine extract is NaCN. It's treated with alkaline ferrous sulfate and acidic ferric chloride overall to form blue or green color, which refers to ferroferricyanide or Fe4 FeCN6 the whole thrice compound, which is commercially called Prussian blue. Next is the detection of element sulfur. Even sulfur is detected by lysine extract. Here, sodium reacts with sulfur to form lysine extract of Na2S. The conformity test is the lysine extract reacts with sodium nitroprusside, giving a deep violet color. Or the other reaction is the lysine extract could react with lead acetate in presence of acetic acid, giving a black PPT. Now, you have to remember that this deep violet color is due to formation of which compound, and the black PPT in the lead acetate acetic acid test is due to which compound. So for that, let's understand the reaction. So first, sodium nitroprusside reaction. The lysine extract is reacted with sodium nitroprusside. Look at the formula of sodium nitroprusside. It is Na2FeCN5NO. Sodium nitroprusside is Na2FeCN5NO. Now, this particular complex IUPAC name could also be asked. This particular compound has the IUPAC name as sodium cation. Then in the anionic complex we have 5 cyano, so it will be pentacyano. Then nitrosyl. Remember, the nitrosyl is a positively charged ligand with a +1 charge, and the anion contains iron, so it will be ended with ferrate, and the oxidation state of Fe is +2. So overall, with no gaps, the compound name would be sodium pentacyano nitrosyl ferrate. If I talk about the oxidation state of nitrosyl, then as already mentioned, this is in +1 oxidation state. The CN5 overall would have -5 charge, and the overall complex has a charge of -2. So if I have FeS plus 2, then plus 2 minus 5 minus 3 and plus 1 would give -2, which corresponds to the -2 charge of the complex. So now, once again, the lysine extract reacts with sodium nitroprusside having a formula Na2FeCN5NO. Na2FeCN5NO reacts and gets added up to form Na4FeCN5NOS. Now here, the NOS is the isothiocyano ligand, and this is a negatively charged ligand with a -1 charge. The CN5 again would correspond to -5, and this is also the same oxidation state of +2. So +2 -5 -3 and -1 would give -4, and this refers to the -4 charge of the anionic complex. So even the oxidation states of the ligands could be asked. You need to remember this. So coming back to the reaction, the Na2S reacts with Na2FeCN5NO sodium nitroprusside to give Na4FeCN5NOS, which has a deep violet coloration. The IUPAC name of this compound is similar to the previous one, but instead of nitrosyl, now we have isothiocyanone. Hence, the compound would be named as sodium pentacyano isothiocyanone ferrate in the +2 oxidation state. The alternate test is the lysine extract reacting with lead acetate, and this lead acetate is reacted in the presence of acetic acid, giving a black precipitate of lead sulfide along with twice of sodium acetate. So, in the nutshell, the deep violet color was due to the complex Na4FeCN5NOS, and the black precipitate in the detection of sulfur is due to lead sulfide. Next is the detection for halogens, and the detection again is done by using lysine extract, and here the sodium reacts with the halogen to form sodium halide as the lysine extract. In the confirmatory test, the lysine extract is reacted with silver nitrate along with HNO3. Now, on reaction with silver nitrate in presence of nitric acid, if there is a formation of white precipitate and it is soluble in aqueous ammonia, which is ammonium hydroxide, it confirms the presence of chlorine. And obviously, the white precipitate over here corresponds to AgCl. The white precipitate corresponds to the formation of silver chloride. Similarly, if there is a dull yellow precipitate which is partially soluble in aqueous ammonia, it would confirm Br, and the dull yellow PPT would correspond to AgBr. Similarly, the yellow PPT insoluble in aqueous ammonia confirms I, and obviously the insoluble precipitate would be of AgI, that is silver iodide, AgI. So AgCl is white PPT, AgBr is dull yellow PPT, AgI is yellow PPT. Now between Br and I, it is the solubility which will decide the corresponding halogen. If the PPT is soluble or partially soluble in aqueous ammonia, then it is bromine, and if it is insoluble completely, it is iodine. One important point to note over here, the nitric acid is used over here because it would decompose the sodium sulfide or sodium cyanide lysine extract if at all it is formed. So if it is only the individual detection of halogen, we don't want the sulfur and the nitrogen to interact, and that is why the HNO3 is very crucial over here, because it will decompose sodium cyanide and sodium sulfide if at all they are formed. So HNO3 in the detection of halogen is used because it decomposes Na2S and NaCN if it is formed. It decomposes. And the reaction is quite simple. Sodium halide reacts with silver nitrate in presence of HNO3 to form a silver halide PPT. If it is the white PPT of AgCl, it dissolves in aqueous ammonia, giving a complex of AgNH3 twice Cl. Obviously, the solubility is due to the formation of this stable complex. AgPr will react with ammonia to form a partially soluble complex of AgNH3 twice Br. And AgI, the yellow PPT, is insoluble because the complex is not that stable of AgNH3 twice I. Now the combined detection of nitrogen and sulfur. So for nitrogen and sulfur together in the analysis, we need to prepare a lysine extract of sodium thiocyanate, which is sodium reacted with carbon, nitrogen and sulfur on heating forming NaSCN named as sodium thiocyanate. The confirmatory test is similar to nitrogen. As in test for nitrogen, instead of green or blue color of Prussian blue compound, here in the nitrogen and sulfur together, there is blood red coloration which confirms the presence of nitrogen and sulfur both. And the corresponding reaction is the lysine extract of NaSCN reacts with ferric chloride and gives FeSCnCl2. So the blood red color is due to the formation of this complex, which has the IUPAC name as thiocyano, the ligand, ion in the +3 oxidation state, and the anion chloride. Thiocyano ion 3 chloride. And this chloride, this complex has a blood red coloration. And the last is the detection of phosphorus. For phosphorus, the detection is done by reacting phosphorus with sodium oxide. Phosphorus with sodium oxide. And on boiling with sodium oxide, it forms sodium sulfate. On boiling with sodium oxide, it forms sodium phosphate, that is Na3PO4. Na3PO4. The confirmatory test is sodium is boiled with nitric acid and is then treated with ammonium molybdate, that is NH4 twice MoO4. Ammonium molybdate NH4 twice MoO4. The formation of yellow precipitate indicates the presence of phosphorus in organic compound. The formation of yellow precipitate indicates the presence of phosphorus. Let's see the associated reaction. The sodium phosphate which is formed in the detection, the sodium phosphate formed reacts with nitric acid to form phosphoric acid and sodium nitrate. The phosphoric acid in turn reacts with ammonium molybdate in presence of nitric acid to form a yellow precipitate of ammonium phosphomolybdate. Ammonium phosphomolybdate. And the formula is NH4 thrice PO4.12MoO3. The important point to remember is the yellow precipitate formation in the detection of phosphorus along with byproducts of ammonium nitrate and H2O. So as a summary, here the phosphorus is detected by reacting the phosphorus with sodium oxide forming sodium phosphate. The sodium phosphate in turn reacts with HNO3 forming phosphoric acid, which reacts with ammonium molybdate in presence of HNO3 and finally forms ammonium phosphomolybdate, which is a yellow precipitate. That's all for the qualitative analysis of organic compounds.